Welcome to the Space Society at Imperial. I am Liam and I'm the chair of the Space Society this year. And today you're going to get a presentation from all of these wonderful people about the projects that we put on and run throughout the year. So I could stand here and talk forever about the fancy posters that's behind me, but I will hand straight over to the actual project leads so that they can give you a bit more information about the projects that we run, so that hopefully by the end of the day, you can decide which projects you want to get involved in and how you want to stay in touch with the society throughout the year. So without further ado, over to you, Theo.
It's me. Hello, I'm Theo, PhD Mech Eng. I faff around with nuclear stuff most of the time. Which machine are we running off, Liam? This one.
Yeah.
Okay, so I'm here to talk to you today about Project Kepler, which is usually run by Erica Surname. And we are looking to build the thrust-to-weight ratio record-setting rocket engine. There's a lot of caveats in that. So basically, we're looking to build a rocket engine that's going to be producing to be producing about 25.4 kilonewtons, or 2.5 tons of thrust, powered by liquid oxygen and isopropyl alcohol. Why isopropyl alcohol? I always get that question. Why don't you use kerosene? Well, isopropyl alcohol is unregulated. We're looking to do sort of some stuff that you find on a really big rocket engine, but on a much smaller scale. So this is a mock-up currently made up of, so a lot of you saw it on our store, made up of some real components. All the metal bits you can see are for real. We're missing a lot of plumbing, but it's expensive. And some 3D printed components, which these are currently plastic, but as of today, hopefully we've got a sponsor for our additively manufactured parts. So in terms of the big rocket engine things we're looking to do, this is going to be the only rocket engine, we think, in Europe, designed by students that is using custom turbo machinery. So this is using its own pumps and turbines to generate all the pressure that we need, which means we can get away with lighter tanks while still getting high performance. A lot of these sort of student rocket engines you get at this scale are pressure fed, which if you join the project is something I'm sure you can learn all about and mock ICLR. With that being the case, we're also having to do some things like cooling our combustion chamber with liquid oxygen rather than the fuel, which hasn't been done since the Soviets in the 60s, but we're hoping we can pull it off. And finally, using something called autogenous repressurization, which has been pioneered by SpaceX on the Raptor engine. And we're trying to do it on a bit smaller budget, but we think we've got something that has half a chance of working. And that means that we can save a load of complexity, time and money on sort of pressurization infrastructure for whatever we run. So in theory, it's that kind of thing that makes this rocket engine. We calculated the other day, for the scale of rocket we put this thing on, approximately, we could wave at the International Space Station with it. So join this project and I'll be gone before it happens, but you might be in time to, bond some astronauts. What else? What have we achieved last year? You see, there's a lot of good ticks on here. It's definitely, we didn't just remove the things we didn't achieve. We removed a bit. So we've done a load of stuff with designing a combustion chamber, which now we would redesign, but you learn. We've done simulation of coaxial shear injectors. So if you're looking to look at sort of computational fluid dynamics and multi-physics simulations, which is pretty important if skill for your career. Honestly, I don't know anyone that walks into industry knowing how to use ANSYS Fluent for supercritical combustion simulations. So that's an amazing skill to walk in with. We've got some method spun combustion chamber liners. I didn't have enough hands to bring them down with me. We did a load of studies on our ignition system, and we've decided that we're going to use all 8 at once. We've done the preliminary design for our feed system. You'll see that on the slide in a minute. We've done the design of the turbo machinery stack, and we've even begun manufacture on that, as well as a lot of other bits. We've got preliminary design of our software, and that's going to be a big priority this year, is trying to get the engine control software up and running, because that's going to be a really big step in actually, proving it was safe to fly this kind of thing. But we're not flying it, we're strapping it to a big slab of steel and then lighting it and running away. what are we aiming for this year? We've got a few bits that didn't fit on the last slide that were planned for last year, but we actually got ahead of ourselves, which is manufacturing of all this lot. This year, we've got a big sort of laundry list of things we need to do. So we're looking to get a really big team on this year. And there's a lot of very fun stuff in here. There's a lot of fun stuff in here and a lot of fun stuff in here. So we're going to, our big thing at the start of this year is we want to look at our sort of flow control unit, which is a thing that actually controls the balance of all the propellants into the engine. This is this engine, we didn't put it on the early slides, is running oxidizer rich, which the Soviets found out with the N1 rocket wasn't a great idea, but liquid oxygen is cheaper than fuel. We're going to have a big design review in the first term of the design of our plumbing. Fun. But actually, one of the really important parts of learning to design rocket engines, if you do want to go into a career in aerospace, actually being able to look at a set of pipes and go, nah, is a really important skill. As I mentioned before, engine control software, we're looking to have a pretty much a first prototype of this done this term. We've got some new priorities that may or may come off, but we're really excited that we might be aiming to do a hot test of our turbo machinery unit down at the Silwood Park campus in about March time. So that should be pretty fun. Let's hope it doesn't explode. So yeah, a lot of other stuff in there, which is a bit dull to talk about now. We've got turbine manufacture, which is going to be very cool. So we're going to take one of these. This is a prototype that we did to prove that it was possible. And we're going to be making that of a super alloy. Once there's the worldwide shortage of that alloy stops being a problem. And then we're going to be moving on in sort of first quarter of next year to some of the really fun stuff, which is igniters and really building the mechatronics to make this thing work. Build some tanks as well, so if anyone wants to learn welding, it could be kind of fun. And then we're going to make it go brewer. Is there anything else on these slides? Yes, why should you join? My enigmatic presentation style, the fact that we've got hardware ready to go. So you'll pretty much be working on this thing up until day one. No touching until you're part of the project though, because I'll murder you. Spent far too much time polishing that thing. Yeah, so all of that stuff up there, pretty pictures. We just make cool hardware. If you like cool things and cool things that get very, very hot, the sort of main chamber temperature of that is about 3,500 C. Yeah, come along for the ride. It's going to go, well, it's going to go sideways, but that's the intention. So I'll probably leave it there. So here's some key people. Erica, surname, she never told me how to pronounce her surname, and I don't want to give false information. If you want to join the project, she's always there to answer questions. Groove is going to be our manufacturing lead for this year, so he's actually the one that's sort of looking at procurement and making sure we're doing things efficiently. That's me, Theo. I just sort of basically say that ain't going to work to a lot of things. And Liam, our illustrious chair, used to run this project last year, so we're getting all the funding, right? I'm going to hand over now to you. Who's taking this far on?
Okay, hard to follow that up, but the other mouse.
Green.
Other screen.
This one.
Other mouse, other
There we go.
screen. Got you. Okay, so at Project Sparrow, our mission is to be the first student team to send a spacecraft outside of the solar system. Now, this might feel like an ambitious goal, but granted that we have the right resources in place and the correct industry connections, then there's no reason why we shouldn't be able to carry out this project. And our research is divided up into two main parts. We have the experimental research and the theoretical research. These are some examples of the experimental research we've been carrying out. We developed our own vacuum chamber test rig to test our scaled down prototypes of the sail. We have a team working on electrical prototyping who's developed the onboard computing and is on to testing. And we're also building prototypes of the sail deployment mechanism. And for the theoretical aspects of our research, we have an orbital team who is developing simulations to study how different initial conditions might affect the trajectory of the spacecraft. We have a team working on structural sims who are investigating how we might be able to apply experimental results of scaled down solar sail membranes to larger spacecraft structures. And we're also carrying out some environmental modeling to study how solar winds might interact with the sail and how radiation could affect our electronics.
Okay, so over last year, we managed to get one paper accepted to a journal of British Planetary Society. So it's like a journal which sometimes which often publishes ideas related to space exploration and extra missions. And we got accepted to present at international symposium on solar sailing. So it's like the biggest conference dedicated to space sailing around the world. So it's run every 3 years, and there are people from all the biggest space agencies and reporting their results. And apparently we were also getting so good progress that they invited us. So I can pass around what we managed to publish, and if someone gets a chance, we can see to it, and that's what we are doing. And now let's move on to the next slide. So what we are doing next. Beatrice already mentioned that we got some initial simulation and experimental results, but we need to go and develop them further. So here we managed to figure out that there is some scaling method for solar cells. So basically our idea is that we want to develop methods in which we can run some experiments on scaled down sail with applying desired spin rates and other dynamics, and then be able to have some level of confidence that when we are designing large few meter in size membrane, the dynamics remain the same. So it's a bit similar to like doing experiment for the wind tunnel, where we build small aircraft and it behaves similar to the big aircraft which flies. Next one is we want to work further on orbital optimization. So over last year, we identified that there is high level of uncertainties present in modeling solar sail motion. So there is some crinkling on the surface, and because of that, sail can start turn in some unpredictable way. And aim of that optimization is to identify what are the conditions of mission which enable us to succeed in achieving some desired trajectory, and then identify what potential future missions can take us on board as PDUA missions. And finally, we want to do more prototyping. So we run initial testing in the vacuum chamber, and plan for this year is to develop our testing setup so that we can run experiments with high-speed cameras and be able to have very fine recording of dynamics to do scaling them. Can you give the next slide? So what we are doing next. So we need to work further on the electronics, because for our mission, we will require onboard systems which would enable satellite to go, and those are necessary activities for any space mission to have onboard systems which are sufficient to survive environment and survive the entire mission. Then we need to complete stability analysis. So we are using Julia as our main programming language. So if you want to new, fast, and easy to use programming language, is section for you to join. And finally, today we submitted proposal to Bexus competition. So it's high altitude ballooning competition, when we will try to take our rig for deploying solar sails and fly it to around 20-25 kilometers above the ground, to be at the verge of the space, let's say, so that density of air is small, and deploy membrane way bigger than we can in vacuum chamber. And okay, so last year during conferences, we managed to establish some relations. So right now we are talking with Breakthrough Starshot, so it's like organization which has a lot of money to fund related research related to solar sailing, and they want to support us in our endeavors for the coming years. And finally, we want to have better models of structures. So we will be working on something called energy momentum method for modeling structures. So it's like a quite novel approach to finite element modeling, where we want to conserve both energy and momentum in our finite element solver. So we want to have some industry relevant experience in developing codes for modeling spacecraft structures and doing it in a very like systematic manner, then we invite you to join us. So now on to next question.
Just like say quickly, if you're new to like first year new to academia, the fact that Spark is a publication and upcoming ones, it's like really big. That's really big. So introduction for ourselves. My name is Philip. I'm this year's IPRL manager and strategy officer for the Rover project.
And I'm Ryusei. I'm the manager and electronic engineer for this project.
For the Rover project.
For the Rover project, yeah.
So wait, which one is it?
Yeah,
this one, I guess. So we are IPRL. You might some ask like, what is IPRL? What's ICSS? IPRL is part of ICSS. We are also a joint project with the Robotics Society. We've been running for just a year, and our aim is to create a hub for students who are interested in planetary robotics and space exploration of like, let's say, surfaces and planets, to come together and develop projects, not only for competitions like usually in second, but also for research. So basically the aim is just to get people around actually like this very specific area of space and just, build the connections, share the experience, and share the projects together. This one. Okay. So how we intend IPRL to work in the long term. So we want to have kind of an organization structure that supports many projects. So with these projects can be both for competitions, for research, for masters. Our secret aim and dream is to also publish at EAC 2024. However, we do have our flagship project, which we've been running for last year, which is the competition of the project, which Ryusei will tell you about in a second. So that's been our main focus last year, just to get experience, resources, just to get the team, building together something cool. And yeah, it's been a very, very tiring year, and Ryusei is here to tell you all about it.
I'm gonna tell you how good it is and not how tiring it was. So our plan this year is to continue working on the rover for a flagship project, and to take part in ERC 2024. We did take part in 2023, which was actually last month. And for our first year, we got top 11 out of 54 participants, and we won one of the tasks, which I will show you in a second. Our plan this year is to make top 8 overall and top 5 in the science tab. So in the competition, they give us 4 tasks to do. One of them is a presentation, which is the one that we won. And the other 3 tasks is we have to use the full capability of our rover to do the tasks that they set for us. So the maintenance, which uses an arm to measure voltages on the panel, navigation, which would be to move around and survey the land, and science, which is to move around the area and also use the arm to pick up rocks for analysis later on. They haven't given us the briefing for next year yet. That will come in April. So in the meanwhile, what we're going to do is we're going to retrofit our rover, which unfortunately isn't here today. But yeah, retrofit our rover and upgrade it so that it's more robust. We have more functionality, as well as other capabilities that we would like to add. So we're planning to do that until April when they give us the briefing. Our team works in a decentralized manner. So we have me and Jimin, who unfortunately couldn't make it here today, who works as a project manager. But our goal is just to see like the top level of the team, and you don't have to like run it by us every time you want to do some kind of like engineering decision. What we do is we meet once a week so that we make decision as a team to do what we want to add to our rover, what kind of capabilities we want to do, how we do it. So this year we're planning to look for 7 or more people for our team. people for electronics, armament engineer, drone payload, suspension and frame, and systems and testing. Even if your role is not set here, please do apply for using our QR code, because it's not like a hard set requirement. If there's more people who are passionate and would like to help out with us, we'd be more than happy to take you. Other than that, if you have any questions, please send us a Gmail, and if you want to follow our progress, follow our links.
And hope to see you somewhere in the fall.
Yeah, if you have any questions, please, you can come call us.
Hello, I'm Thomas. I'm here on behalf of a new and very exciting machine learning research project called Project Stratus, or the High Altitude Ballooning Project, depends who you are. But basically, we are a project that works for a postdoctorate research group using machine learning on stratospheric weather balloons. And then there we go. Right, what is Project Stratus? Well, there we are. What we basically are aiming to do, what the postdoctorate research group does, is it trains an algorithm based on air currents, and using that, it can change the geoposition of a weather balloon by varying its altitude. And we aim to use this for sort of satellite adjacent sort of applications, but it's obviously much cheaper, much more environmentally friendly. We can retrieve the balloon, reuse the parts, and we're not cluttering up space as well. And also, due to angular resolution, we get much better imaging, much better mapping as well. So where are we now? So this is a restarted project that was, generally speaking, just working on weather balloons, but we're slightly more aimed now. So we're still in our infancy. And basically what we're doing right now is we're doing our first launches, programming different sensors. So like our GPS, our temperature sensors to analyze the air currents. We'll be doing our first stratospheric launch within the next month or two. And beyond that is where I think things get really exciting. And we're going to start doing some engineering in order to vary the altitude of our balloon. And we'll just get increasing levels of intelligence in our balloon. So basically, sky's the limit for what we can do with this project. Right, so what we're looking for right now is just people to help us with the C programming of our various different sensors. So if you're looking to develop those skills, this is the perfect place to start. But in the future, we'll be looking for engineers to help us create more and more sophisticated balloons. Thank you.
Excellent. Well, it's hard to follow after everyone else has given some wonderful presentations, but I will do my best. I'm here to introduce the final project that the Society runs, which is perhaps the most standard that you would expect from any space society, and also one of the most well-known, high-powered rocketry. So what is this project? Perhaps unsurprisingly, we launch rockets. You would probably have got that from the name. Specifically, last year, we took part in a couple of launches, culminating in a G-class rocket launch over at the Midlands Rocketry Club. We have a few photos of the rocket and the trajectory that it took shown up here on the slide. So what are we really trying to do? We kind of buy commercial off-the-shelf rocket motors and then aim to achieve some UK Rocketry Association certifications by launching these successfully and successfully recovering them. So as you can see here, we also managed to test our own flight computer, which had GPS tracking and a variety of other sensors as well. So we're hoping to work on that. And as it says at the bottom, last year we managed to train 8 members who had absolutely no experience of rocketry. And in the end, they contributed to the final rocket, which launched to an altitude of about 700, 800 meters, and then successfully recovered under parachute. So if you join this project, what are you going to be doing? Obviously, the bit at the top there, launching rockets. It goes without saying, that's what we're here to do as high-powered rocketry. And as I've already mentioned, we work towards the official UK Rocketry Association certifications for high-powered rocketry, of which there are 3 different levels. We'll mainly be working towards level 1 and 2 this year, just because there are, good building blocks before moving up into the larger rockets, as we try and, make sure we've got all the skills there necessary to lead this project. So we're targeting a J-class rocket motor this year. So for anyone who doesn't know the letters, basically each letter you go up doubles the power of your rocket motor. So J-class is getting pretty up there. It should easily exceed a kilometer, potentially even targeting 2, depending on how well we can design the rocket. And then before that, obviously going to 2 kilometers is quite a task. So what we really want to do is making use of the vast amount of equipment that the Society has literally next door to this lecture theatre. We're hoping to try and launch a few smaller rockets beforehand to build some skills and let you get practical experience and validate all of the work that you're doing throughout the year to hopefully inform the final design of our larger rocket to make sure that it is successful. So that's all from high-powered rocketry. I'll go quickly into some of the other activities of the Space Society before we split off into the Q&A session that is always a big hit every year when we do this. So some of the other activities that the Space Society is involved in, one of the key ones is our annual hackathon. So you can see the photo in the middle there of a couple of little robots on the floor. That was from our last hackathon, where people were tasked in small teams to design a docking mechanism for spacecraft. We then tested these on RC cars to see if something that people had designed in a weekend could actually effectively dock, and they were then graded with the top prize receiving, with the top team in that assessment receiving a monetary prize as well from a sponsor. So alongside running our hackathons, we also try our best to run industry presentations and careers events. So as I mentioned, people on Freshers Fair, we should get Airbus in later this year, hopefully on the 5th of December, but waiting for them to confirm that. And then we also get in a few other companies. So I've been talking to Open Cosmos, Surrey Satellite Technologies, and a few others as well. So hopefully we'll get things like that. And then new for this year, we also want to run a space careers event. We know that lots of people want to get internships, want to get into careers that are actually within the space sector, but maybe don't quite know where to look or don't know how to get started. So I've been involved in 2 of the space placements in industry scheme placements over the past 2 years, and so have a few other members within the society. So we'll be offering some advice and some tips and making sure you're all aware of the opportunities that are out there throughout the year. Then again, at the bottom, we have conferences and outreach. Some of the projects I've already mentioned, but some of our work does end up going to conferences. So you may be able to go and meet various people from industry there as well as we also do outreach events with some local schools and other groups like that in order to just spread the good word about rocketry and space in general. Finally, there's space-themed socials. So this will be everything from watching launches to last year. We also had a movie night where we watched The Martian and a couple of other movies as well. So hopefully those things all sound quite interesting to you. And after this, we will split up into our different sections where you can talk to all of the project leads to find out more information. So if I could have Theo for Kepler over here, so that's the rocket engine project. They'll be down at the front over here for questions. If I could have Svarog, you're already up there, so they'll be over in that section for the solar sail CubeSat. If we could have Thomas for high altitude ballooning up there. If we could have IPRL for the rover project down in this corner. And then finally, high power rocketry will be just here in the middle for me. And then if you want to ask any questions to any of us, please just come along and speak to us. It's fairly informal, so just gather in a group and ask away. And if you do want to become a member, the sign-up sheet is up here. So thank you very much.